Hi guys, welcome back. So this is another data analysis video. I'm still focusing on data transformation. So I made a couple of videos so far about data transformation. One of them looked at imputing missing values, filling missing values, and how that can be used to improve the distribution of a variable. And in the last video, I took a variable that was highly positively skewed, and I demonstrated manually how to conduct various data transformations on that variable, such as the log transform, the reciprocal transform, the square root, the exponential, and the box cox. And then we looked at those to see which ones seem to have improved the distribution of the data better. So which transformed variable or transformed version of the variable would be better to use in some type of general linear model, some type of model that assumes data is normally distributed. So I'm going to do a similar sort of thing in this video. I'm going to use the same variable, I'm going to use the same transformations, but whereas in the previous video I kind of manually typed the formulas in most cases. In this one I'm going to use numpy and the kind of existing functions and methods in numpy. So these are just further examples of how to transform data to make it more Gaussian using transform methods available in the NumPy software library. Okay, so I'm going to start by importing the libraries that we might need. So I'm going to import pandas as PD, numpy as np, matplotlib.py plot as plt, seaborn as sns, and I'll also import scipy.stats as stats in case we use that for anything. And those are the usual nicknames. If you've seen any of these videos before, you'll know that kind of that's the standard thing, and these are often matplotlib and seaborn we'll use for plotting in this case. But I'm going to work with the Titanic dataset again, so I'm going to import the Titanic dataset using pandas and save it as a data frame object called df. A number of variables there. The one that I'm going to, let's look at the info on this so we can see it. So we've got 891 observations or passengers that we have data on here, and a number of different variables. Some of them have got missing data. The one I'm going to focus on here is fare, and if we look at which ones have got missing data, age has got a lot of missing data, cabin's got a lot of missing data, fare doesn't have any. So if we pick on the fare variable, we'll focus on that because we used that in the previous video to transform it. We'll do a similar sort of thing here, but you'll be able to see how much easier it is to perform these transformations using numpy than actually looking up the formula, say online, for a square root transformation and then coding it yourself. And we also know that the fare variable, it needs transforming because it's not normally distributed at all. It's got no missing values though, which is useful, so we don't have to drop any rows. And we can plot the distribution of this variable using we'll use matplotlib. So I'm basically creating a figure and some axis, and we're going to use it. We're going to plot it as a histogram. The fare variable, I'm going to give it the title original distribution of the fare variable. So if we look at that, that's what it looks like. If you've seen the previous video, you'll be familiar with that. It's very positively skewed. Most of the data points are at this end of the axis at the lower value of fare. So most people pay very little fare. Some people paid an awful lot of money to go on the Titanic, probably wish they hadn't. But let's have a look then. So in the previous video, we did these one at a time, and we used a self-defined function to kind of plot them and see what they look like. What I'm going to do here is transform the fare variable by using a square root transformation, an exponential transformation, a log transformation, and the reciprocal transformation. I'm going to do all four at once. So I'm basically going to create new data frame objects, or new variables essentially, and append them to the data frame. So I'm going to call them df square root of fare, and to create that, we're basically going to use the numpy method sqrt square root np.square root, and we're going to pass the original fare variable into the parentheses as the argument to use. So what that's going to do is take every value of the fare variable and perform a square root mathematical manipulation on it, and return a new value, a new vector with a new value essentially. Exponential, similar. The one to notice here, so for df, to take the log of the fair variable, here notice that it's np.log 1p. So if you look, if you go on the numpy documentation, you can look up and see what the different transformations are, what the different methods are, and see what you need to put in. But in this case, we're just taking like a simple log transform, and this is the syntax needed to do it. For the reciprocal, to take the reciprocal, remember that's kind of 1 over the value of the variable of each variable. So it's basically going to take 1 and divide 1 by each value, and that costs where some of the values might be extremely small, close to 0. We have to add this 1 in here, plus 1 here, to avoid sort of this infinity problem where we're dividing by 0, which is mathematically undefined. So let me run that. That has transformed all of these, and if we now call df head, you can see it's kind of appended these to the original Titanic data set so that we'd imported. So there is our original fair variable in this column. There's the square root of fair, the exponential transform of fair, log of fair, and reciprocal of fair. So let's just extract these 4 transform variables there. So let's create a new matrix, a new data frame object. We'll call it fair underscore tr for transformed, and we'll just pass a list including those 4 variables to it. So if we do that, these are the things we're interested in, these 4 transform variables. So what I'm going to do now is, we've transformed them. We want to know which one's the best in terms of improving distribution of the variable from this, the original distribution, highly positively skewed, nowhere near a normal distribution. So which one does the best job of this? And what I'm going to do here is I'm going to use our new fair underscore tr data frame, use the .hist method on it, ask it. I'm going to specify one bin size is about 20. And I'm asking for a layout, a 2x2 layout. So it's going to basically give us a 2x2 layout of histograms. And I've specified an age color of K, which I believe is black, and a fig size. Given the whole thing super title, that's kind of the title for all 4 plots that are going to be displayed. Transformed fair variables. And then let's run plt.show. Let's look and see you'll see what that code has done essentially here. It's basically created a 2x2 layout of plots. So you can see there the square root transformation has shifted it to the right a little bit, but it's still very positively skewed. It's not made a big difference compared to the original. The exponential, I would say, it hasn't really done a great deal. That's kind of probably even worse now, the distribution here. The reciprocal, the same. It's not had a great impact really. It's not made our data look our fair variable look more normal. But the log transform seems to have improved it dramatically. If we consider it to be kind of roughly normal like that, it's far from perfect, but we might be able to. It would certainly be better to use this log transform version of the variable in a model that might require normality assumptions. Okay, and this last cell here, I'm going to get descriptors for the reciprocal fair. So we use the reciprocal transformation of the fair variable, and hopefully, if I run that, it just gives descriptors. You can see that adding 1 to the formula. Remember, I specified up here. Need to put this +1 in here to avoid this infinity problem. Adding 1 to the formula, it seems to have made the formula valid, and the max is now shown as 1 maximum score on our reciprocal variable rather than infinity. That was the problem before. If I take that +1 out and run it, what you'll find is we'll get these 3 plots, but this one will be empty, and we'll get a message telling us like the scale runs from like 0 to infinity or something like that. Okay, so let me change that spelling. We've avoided the issue of dividing by 0 by adding a +1 on the reciprocal transform. That was just to clarify that point. Why is that on there? But the key thing to remember here is if we were needing to include our fare variable in some sort of model, maybe a logistic regression model, we want to see how fare predicts whether someone survived or died. We're probably better using this log version of fare. What that means though is we're not using the original data. We have to make sure it's clear that it's the log of fare but not fare itself that we're using as a predictor. So it's worked reasonably well in this case, but what I often find is that data transformations, you can try them, but they don't always work. So there are other things, other analyses that you then would have to use that don't necessarily assume that data is normally distributed. Okay, so this is the last video I'm going to make about data transformations for now. I'm going to stop recording in a sec. Next few videos, I'm going to move on now in the next few videos and start demonstrating how to perform ANOVA, so those kind of parametric statistical models that compare multiple groups and interactions between them, quite commonly used in experimental designs in disciplines like psychology. Hopefully this was useful and interesting, and it kind of just reiterates what I've covered in previous videos about data transformation, but much easier to do in terms of the coding required using numpy in this case. Okay, thanks for listening.